Hey guys, I'm going to do a video on the mole, the relative mass scale, molar, and molecular mass. Now these topics can be a little confusing to start off with, but you really need a strong grasp of them to do well in chemistry. So let's begin. The mass of an atom depends on the number of electrons, protons, and neutrons. Knowing the mass of atoms is very important in chemistry because it allows chemists to predict reaction yields and is vital in analysis of unknown compounds. Atoms are so tiny that it's impossible to weigh them individually. So what do? Well, it is possible to experimentally determine the mass of atoms relative to each other. But relative mass scales do us no good if we don't have a standard. We need a standard. Atomic mass is defined as the mass of atoms in atomic mass units, aka AMU. 1 AMU is defined as exactly equal to 1/12 the mass of the carbon-12 atom. So why do we choose carbon and why do we give it 12 AMU? Well, Emilio Avogadro from the 18th century was able to experimentally determine the number of atoms in a given mass of carbon-12. So why do we give it 12 AMU? Well, it was experimentally determined that carbon-12 is 12 times as massive as hydrogen. Hydrogen is the least massive element. This allows the smallest element, hydrogen, to be 1 AMU, which sets us up with a very neat relative mass scale. Alright, let's talk about the mole and Avogadro's number. It is impossible to weigh single atoms, so we deal with macroscopic samples. They contain unimaginable number of atoms. Unimaginable but not uncalculable. We need a unit. In the SI system, the mole, the symbol is MOL, is the amount of a substance that contains as many entities as there are atoms in exactly 12 grams of carbon-12. I'll repeat that. The SI system, the mole is the amount of a substance that contains as many entities as there are atoms in exactly 12 grams of carbon-12. Why 12 grams? Again, 12? Well, it sets us up for something called molar mass, which I'll talk about in a second. So, let's go to Avogadro's number. So, the number of atoms in 12 grams of carbon-12 is 6.0221415 times 10 to the 23. I can't even pronounce that out of scientific notation. So this is just a number. It's a mole, and it's also called Avogadro's number. It's just a number, just an amount. Just as a dozen eggs is 12 eggs, a mole of eggs is 6.022 times 10 to the 23 eggs. So, I was saying 12 grams of carbon is the benchmark for the mole, 12 grams of carbon, and we're like, why is it 12 grams? Well, here it is. We can deal with large amounts of atoms using the mole and carbon as a standard, and we know the masses of atoms relative to each other. We can now determine the number of atoms and molecules in any given mass of a known substance. Okay, molar mass is defined as the mass in grams of 1 mole of units of a substance. This should be of a substance, and the units is gram per mole. If we look at the periodic table, what do we notice? Well, atomic mass is exactly equal to molar mass. And why? Because we set 12 grams as the mole of carbon-12, which has 12 AMU. Therefore, the relative mass scale will follow it to a T. You'll notice slight discrepancies because the molar masses of elements have been averaged for natural abundances. We define the mole as a number of atoms in 12 grams of carbon-12, whose atomic mass is 12 AMU. So atomic mass equals molar mass in number but non-units. Atomic mass is in units of atomic mass units, AMU, and molar mass is in grams per mole. We cannot weigh individual atoms, but now we can determine the mass of atoms theoretically. Knowing the molar mass, the atomic mass, and Avogadro's number allows us to calculate the mass of the individual atoms. So let's test it out. We're going to use carbon, of course. So, example, 12 grams of carbon-12. We're going to divide it by Avogadro's number because that's the amount of atoms in a mole, which is 12 grams because we know the molar mass, carbon is 12. So, if we divide 12 grams by the amount of atoms in a mole, which is 12 grams, we're going to find the mass of an exact atom of carbon-12. Which gives us this value, which is 1.993 times 10 to the negative 23 grams. That is the mass of a carbon-12 atom. So let's test relative mass scale. We know carbon-12 is the 12th massive atom on the periodic table, and we know that hydrogen is the first. So hydrogen is exactly 1/12 the mass of carbon. So let's test it out. We should be able to divide carbon's mass by 12 and get the mass of hydrogen, which is also equal to 1 AMU. So let's divide by 12. 1.993 times 10 to the negative 23 divided by 12 equals 1.661 times 10 to the negative 24 grams. Then we're going to get the molar mass of hydrogen, which is approximately 1. Remember, natural abundances kind of mess with the numbers. Divided by 6.022 times 10 to the 23 equals 1.661 times 10 to the negative 24. These two numbers are the exact same. This proves the relative mass scale. So therefore 1 AMU equals exactly, well, approximately, 1.661 times 10 to the negative 24 grams. For a final mental test, carbon equals 12 times hydrogen. So if we get carbon over hydrogen, we should get 12. So if we divide the mass of a carbon atom, 1.993 times 10 to the negative 23, by the mass of a hydrogen atom, 1.661 times 10 to the negative 24, we should get a number that's been very popular today, 12. Thank you.